Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on February 7th, 2026, exactly 1 week ago. It details how LinkedIn successfully deployed large language models for real-time search ranking at an industrial scale, achieving a massive 75 times boost in ranking throughput, while significantly improving search relevance. The paper is titled, Semantic Search at LinkedIn. And as we'll see later, the specific architecture choices they made to cut down latency are really impressive, offering a clear roadmap for efficient AI in production. So, Figure 2 illustrates the relevance training pipeline for this small language model ranker. The process begins at the top, where a large model teacher undergoes supervised fine-tuning on reasoning tasks using long prompts to build strong domain understanding. This capability is then distilled into the smaller student model shown in the middle row, followed by soft label distillation, where the student learns to predict simple one-token outputs from the teacher. Finally, the bottom section shows the model undergoing list-wise training to produce the final ranker, which optimizes the actual ordering of search results. So, while the previous figure zoomed in on relevance, Figure 1 maps out the complete multi-teacher ecosystem. At the top, the hierarchy starts with the 8 billion parameter sage judge training a relevance teacher. This pairs with a multitask engagement teacher to jointly distill knowledge into the compact 0.6 billion parameter student model in the center. The bottom half shows how they manage inputs. They use reinforcement learning to summarize user history and an embedding model to compress document text, keeping the context short for the small ranker. Alright, moving from the architecture to the results. Table 1 breaks down exactly which techniques drove performance for the job search model. Starting near the top, the baseline using standard ordinal labels achieves an NDCG score of about 0.76. But notice the first major jump. Switching to soft label supervised fine-tuning instantly boosts performance by over 11% because it captures probability nuances better than hard categories. Scanning down, adding ranking loss and upgrading the base model steadily pushes the gains to around 18%. The most dramatic leap, however, comes from scaling the data volume by 40 times, which skyrockets the improvement to nearly 25%. Finally, the last row reflects the production trade-off, where adding summarization and pruning dips the score slightly, but secures the speed needed for deployment. Similarly, Table 2 tracks the performance gains for the people search model. The baseline open-source small language model starts with an NDCG at 5 of roughly 0.81. Initial techniques like domain reasoning and soft label fine-tuning provide steady growth, reaching about 3.5% improvement. But notice the massive leap when ranking loss is applied. This single addition more than doubles the accumulated gain to over 9%. Finally, distilling from the relevance teacher caps the total improvement at just under 10%. Well, while the previous tables focused on quality, Table 10 reveals the critical efficiency breakdown on a single H100 GPU. The first row shows the full text model. It yields the highest relevance score of 0.94, but suffers from low throughput, managing just 290 items per second. In the middle row, applying summarization and pruning improves speed significantly, jumping to 2,200 items per second. However, the bottom row shows the real game changer. The mix LLM architecture skyrockets throughput to 22,000 items per second, which is a massive 75 times speedup over the baseline, with only a marginal drop in ranking quality. Okay, reducing model size is only half the battle. Table 12 details the optimizations that push the pruned model to that 2200 figure. Starting from a baseline of 750 items per second, the first big jump comes from scoring only prefill execution. This step, which bypasses the slow generation phase, adds 400 items per second. Another major gain comes from in-batch prefix caching. By processing shared query instructions just once for the batch, they squeeze out another 400 items per second, eventually hitting the final target. So, putting those optimization techniques into practice requires a robust infrastructure, which Figure 5 maps out in 3 distinct layers. At the top, the retrieval layer ingests the search query and manages initial retrieval using a CUDA accelerated hosted search. The process then flows down to the serving layer in the middle, where the ranking mid-tier coordinates the traffic. It pulls fresh signals from the feature store and dispatches candidates to the inference service for final scoring. Supporting all this is the feature generation layer at the bottom, which uses Spark and Flink pipelines to continuously refresh the embeddings that feed the model. Wrapping up, 2 key takeaways stand out. First, multi-teacher distillation successfully transfers complex reasoning into compact models without losing quality. Second, strictly optimizing for inference, using techniques like the prefill-only mix-LM architecture, enables industrial-scale deployment. This combination proves that large language models are ready for real-time ranking systems. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.